As we know, assessing the soil variability and addressing this variability is the key to precision agriculture. Reliable assessment of our soil resources using advanced techniques like deep learning and digital soil mapping will definitely help us to utilize this resource sustainably for improving resource use efficiency in agriculture. So keeping this in view, the third lecture will be delivered by Dr. Buddhiman Minesne, Professor Soil Landscape Modeling, University of Sydney, Australia. Dr. Minasne is recognized as a leader of digital soil mapping and modeling. So we are eager to listen to you, sir. With this background, may I invite Dr. Minasne to deliver his lecture on soil landscape modeling for enhancing resource use efficiency in agriculture. Over to Dr. Minasne, sir. Thank you.
Thank you.
Thank you, sir.
Thank you. Thank you for the organizer. Thank you for inviting me. Thank you for the nice sessions you have today. So I'd like to share my screen now. Okay, thank you. And yeah, hope you can hear me well.
Yes, sir, you are audible and your slides are also visible, sir.
Okay. So Dr. Chowdhury asked me to present something about physical modeling. So most of you know maybe my work in the digital soil mapping. So, but I also started in the soil physical modeling. So I'm thinking about how this presentation is how we combine this empirical and process-based modeling, empirical and mechanistic modeling. And as this series is about enhancing resource use efficiency in agriculture, I will try to show some example about empirical and mechanistic modeling. So I would like to acknowledge my colleague, Dr. Federico Maggi from University of Sydney, and Chiara Pasut from University of Sydney, and Dr. Rudianto from University of Malaya in Malaysia. Okay, so we know that there are different soil models. So this is a classical diagram long time ago in 1993. Some of you may remember, some of you may not know this. So what it's saying that there are different types of models. There are qualitative models and there are quantitative models, qualitative models that you can express in the field. Soil scientists like to do. They observe things and they describe it in soil horizons, in pads, aggregates, and so on. And there are qualitative, there are also qualitative mechanistic models, such as a Yenis model that you say that soil is forming as a factors of soil formation. There are some processes that are happening, but you describe it qualitatively. But there are also qualitative functional models or qualitative empirical models that you say that if this soil occurs here, then it should do something like this. This is empirical models that we observe in the field or describe. But for our purpose, we like to do more of quantitative models, because quantitative models, we can give a indication, we can give more precise values, and we can address many scientific questions. And the scales also depend on different types of scale. So whether it's in the pattern or profile in the field, go up to country, region, continent, or the world, or you can go down from the soil horizon down to molecular level. Right? So there exist different types of models. So in this presentation, I'll touch on the two models. One is empirical models, and this is mainly pedotransfer functions and digital soil mapping. So pedotransfer functions links from one soil properties to the other properties, usually the one that is more difficult to measure, such as hydraulic properties, water retention, hydraulic conductivity. And digital soil mapping is that we try to map these variables that we are interested in space. Right? So this is all based on statistical relationships. I mean, we have observations and then we make statistical relationships relating what we want to predict, either spatially, either in the field, based on something that we can measure very, very cheaply. For example, remote sensing images, it doesn't take a lot of effort. You just download it and it's available throughout your area, your field. Right? So it's based on statistical relationships, and the larger the training database, the larger the observation, the training database, the more useful the model is, the more robust the model, the more applicable the model is. And sometimes people use machine learning methods that are different machine learning methods, right? And in contrast, mechanistic models such as Hydrus that you learned this morning is based on a process-based relationship. It is based on the law, on the transport laws that based on this water retention characteristics, this is how much water the soil can hold or can transmit. And the good thing is that you only need small database for calibration. That means that if I know the hydraulic properties, I can predict what is going to happen if it rains, how much millimeter of water, and it can be extrapolated, quite readily extrapolated. That means if my model is built here, I can apply it in India, in any place else in the world. All right, so let's talk about the empirical models that the digital soil mapping. So this is usually it's based on soil data, soil observations data, point observations data. People went out and did soil survey with point observation or soil maps. And we relate it into raster database that is collected by satellite data. So we have these observations and we relate it into what is remote sensing tells you about the soil. It can tell you about the reflectance, it can tell you about the elevation and so on. And you relate this through machine learning models that relates these observations with the environmental variables. This is sometimes called the Scorpion factors or the soil forming factors. You can information about the soil, about the climate, about the relief, about the parent material, about the hydrology and so on, and you put it in the machine learning models and it gives a prediction about the likely, based on these few observations, you can predict for the whole area and some uncertainty of the estimate that tells you how good your map is, right? So this is very easy, and what is it? It's a statistical relationship. It's rapid. Once it's calibrated, you can predict everywhere. And it's scalable. That means that if based on this relationship, it doesn't matter where you go. It comes from the field to the region to the continent or all over the world, right? So it's relies on big data. If you have lots of data, big data, you can extrapolate towards the world. But the thing is that there's no process understanding that we don't know what's happening. We only rely on the machine learning or the statistical relationship that tells us based on this observation, I can predict the carbon stock of the world, right? So this is just an example that we did based on observations, thousands of observations around the world. We relate it with the climate, with the topography, with the parent material, with the satellite images, and we predict the carbon stock in the world. So this, it makes sense. In the tropics, you have high carbon stocks, and then in the dry region, you have smaller, and near the coast, you've got higher carbon stocks. The pattern makes sense. The pattern follows the rule about climate and relief, but we don't know the mechanism that if you try to ask the model, so why does it predict like this? The model doesn't know. So it's just a statistical relationship, right? So what we can do also that we can relate it with more dynamics. Then we want to know how does the soil carbon change with times. So we can model that rather than running mechanistic model, we run a simple empirical mechanistic model. So based on observations, we run a prediction of where does the land cover change. We know that when land cover change, that means that you lose or increase the carbon stock. And when does it change? From what land cover to what land cover, that tells you whether you gain carbon stock or lost carbon stock, and how long has it changed. We can model that based on satellite data, and based on that we can calculate how much carbon has changed throughout the world, right? So in this example, we calculate the baseline at 2001, and we can do the simulation and what that's tell you us in what's happening in 2016. Right, so for example, in the area of Brazil, this is the area that's 2001, is still forest. And then the Landsat in 2013 says that this area here has been has been deforested compared to here, and this area here, the deforestation has increased. That means that we expect this is the soil carbon, that we expect the carbon to decrease in this area because of deforestation, right? So based on the land use, the land cover change and how long has it changed, we can calculate how much of it changed over the world. So for example, in 2001, we estimate the topsoil, we got about 790 petagram or billions of tons. And then after 16 years, most part of the world or different parts of the world, there is a decrease in 1.9 petagrams of soil carbon, or in other words, there is a decrease about 2 per mil, 2 per 1,000 out of the original stock within 16 years. Within each year, although the decrease is quite small, but it's reasonable over time. Then you have a lot of decrease, and a lot of the decrease in the tropics and subtropics, right? So because this is an empirical model, we can model it, although it takes a while. It's reasonable. We can model it all over the world, and the prediction can give us indication about how much area that has lost carbon, and so on, how much of it is the critical limit, and so on. Right, so this is empirical model, right? So it's scalable. That means that you apply anywhere in the world. Once it's calibrated, you can apply anywhere in the world. So mechanistic models is something different, right? So well, it's something like what you heard this morning about hydros. So, but hydros mostly deals with water flow, but we can do much more about that. So usually it can partition as well, not just about the soil, but also the atmosphere. And you can model how much of it is rainfall, and and then the solar radiation, that's how much it gets. And then it can go into the soil. So in the liquid, in the aqueous complexation, in the gas phase, whether it's absorption or desorption, if there's any biological process or a mineral process, all of this can be modeled based on mechanistic principle. So one of this newer version of mechanistic model, this is called BRT-SIM. So this is the site, and it's coded in MATLAB, but you don't need to know a lot about MATLAB, but you can run it. So it's a mechanistic model using mass and energy conservations and continuity laws, and it can be solid, liquid, gas, and also biological substances, chemical, biological, and it's either 0D or 1D or in a profile, and you can make it 2D or 3D by running it at different places, which will show an example later. So using this, it has all the basics equation, that is the continuity equation on liquid, gas, and heat. And also it's a you can incorporate on the transport of these dissolved materials, and it can model kinetics and so on. All right. So using this kind of mechanistic model, we can actually run it spatially. That means that you can run it not just at one location, not just a representation of one field, but you can run it at representations of different fields, right? So what do we mean? That if we have this model defined at the whatever reactions we want to run, to simulate, we can run it, and let's say that one of this is one profile, and we can represent that profile as a location in the map, right? And we just need to run that multiple locations, although independently. We can make a representation of, because of the spatial variability of the soil, we can run it multiple locations, and it can be in the field or in the states or in the whole continent or in the whole world, right? So, and because it's a process-based models, it has a valid extrapolation because it's based on physical relationship. The downside of it is that it has a large computational time. That means that running one model, full simulation model at a pixel, it probably takes few minutes. But if you want to run it for the whole country, that is how many pixels, thousands of pixels, or maybe millions of pixels, then the timing gets very high. That's why we need a high performance computer to run it parallel. Right. So, for example, we'll just show them some example. In a soil water model, similar to HYDROS, you have the profile and you discretize it, and then it's based on Richards equation. Solving this Richards equation, you have water, and then and how does it transport, right? So one of the requirement to solve this Richards equation, one of the requirement of any model, is estimating soil hydraulic properties, right? So the most famous hydraulic properties or water retention curve is, of course, the Van Genuchten model, which we heard about this morning. But one of the limitation of the Van Genuchten model, if you remember, is this the theta r value, the residual water content. That means that with that residual water content, the water content always go towards theta r. There's no it doesn't reach zero even if you extend it up until complete dryness. If you increase it, because it only goes to theta r, right? So that's one of the limitation of it. And as a consequence, in the hydraulic conductivity in the Moellem-Van Genuchten model, that the hydraulic conductivity drop off very quickly because it's mainly modeling a capillary flow. It mainly models capillary flow. But on the actual data, you can see that water retention doesn't just plateau off. It goes slowly, and it goes off slowly towards this is oven dryness. And then the hydraulic conductivity also doesn't drop off immediately, but it goes off, drop off slowly because of the film flow, right? So people know about this limitation long time ago. So this is in 1991, based on the Campbell model. What they tried to do is then they added up two functions. One is to represent capillary flow. One is to represent the absorption or the film flow, right? So this is not new. And this is what we call as additive model. So you have the capillary models. This is the usual Van Genochten model. And then you have add another function that is to do with the adhesive force of the water at the dry end. And in the hydraulic conductivity, you model the conductivity of the capillary flow and the film flow, right? So this has been done. And if you do this kind of models, the thing is that it gets very complicated. And then you have something like this condition. If, for example, for the pressure head less than this, use this function. If not, then use this function because of this. It gets very complicated. And then you get additional constants that makes it more difficult to parameterize, and you get more difficult to parameterize. So we look at another type of model rather than the additive model, what we call as a scaling model. The scaling model is that you multiply two rather than you add two functions, you multiply two functions. So for the water retention, you multiply the saturation index with the saturated hydraulic conductivity. But the saturation index itself is a function of two functions. One is modeling the capillary flow, and one is modeling the adhesive water retention. Similarly, at the hydraulic conductivity, the relative hydraulic conductivity is a function of the flow due to capillary and the flow due to film flow, right? So it looks very complicated, but what it does is showing that if compare with the original Van Genochten model, which has 4 parameters for water retention plus 2 parameters of the hydraulic conductivity. This kind of scaling model maintains that it's also 4 parameters plus 2, 4 plus 2, and while other kind of model, you can start increasing the number of parameters, right? So a bit of the equation is looks confusing, but it's not confusing. It's quite simple. So when you have the water retention, what you have is water content at a particular potential is a function of the saturated water content times the saturation index. And this saturation index is made up of two values. One is this gamma, which is what is the conventional water retention function. And then the other factor is trying to model under dry condition, so that similarly this hydraulic conductivity is 2 functions. One is the usual function, this gamma function, that is the modeling capillary flow, and the other one is modeling so that it goes in the dry condition, right? So this is just showing how it's different from the Van Genochten model. So using that, we can see that this is the Van Genochten model, which dropped off very quickly, the effective saturation. And then the hydraulic conductivity also dropped off very quickly because it doesn't model the capillary flow. While the newer model, we call it the FX model, because it's due to Fretlet and Sink, and then the conductivity is due to Wang. So the FXW model, that it models both capillary and adhesive forces. So the water retention, it drop off more slowly, and the hydraulic conductivity as well, it drop off more slowly because it models the film flow, right? So using this, we fitted the data of the Ansoda database with this new model, the FXW model, the scaling model, and then compared with the Moellam Van Genochten model. We can see that it fits well, especially at the dry end. And then the things that it fits well is the hydraulic conductivity. As you can see, the hydraulic conductivity at the dry end, the Moelom-van Genochten model doesn't fit quite well, right? So this is just an example of the clay soil. So this is going up to dryness. So if we fit it, the red one with the Van Genochten models, it tends to drop off, and then the resulting is that the hydraulic conductivity is much smaller than what it needs to be. And similarly, it also behaves differently at a different condition. Right. So we want to model this tortuosity factor. One of the hydraulic conductivity is this tortuosity factor. And the tortuosity factor, it depends on the texture, and it's more defined on the loamy soil and the sandy soil. You have a more definition of the tortuosity factor about how water flow. But if you are a more fine texture soil, clay or silty clay, then the definition of the L values of the tortuosity factor is more undefined, and it's more difficult to predict. So using that, we can now make a pedal transfer functions predicting these new functions. We call it neuro-fx, due to the fx function, the Fredholm and Singh functions. So using sand, silt, clay, and bulk density, we have a neural network, and it predicts the water retention and also predicts the hydraulic conductivity. So this is the new pedal transfer functions that's predicting the water retention and hydraulic conductivity. This is the Rosetta functions. Of course, we show that our model, the pedal transfer function, can predict better in this condition. So now what can we do about this? What we can do is we can make a prediction and uncertainty. We can map these parameters throughout different regions. In this example, we map it for the US continent and at a different depth. And this is saturated water content, alpha, M, and saturated conductivity, and so on. So using this, we can spatialize it. That means that based on the digital soil maps, we have based on digital soil maps of sand, silt, clay, and bulk density, we'll apply up these pedal transfer functions to the map so that we can do a simulation. So this is published recently, and you can read about it, and or if you want it, you can email me. I'll send you the copy of it. So we show that at the pedal transfer level, we can make this pedal transfer function. So, but how do we use this more towards a larger scale, right? So in this example, we do predictions at a global scale, but of course, you can do it at a continental scale or a field scale to be more relevant. But this is just showing that using mechanistic model, we can infer a lot about what's happening at the global scale, right? So like before, so we translate this pedal transfer functions into maps of this. So these are the projecting the parameters of the water retention and hydraulic conductivity curve throughout the world, right? So what's the use of that? So that we can run simulation models, right? So we can run mechanistic models all over the world, of course, at very coarse resolution, at 10-kilometer resolutions. But we want to simulate what's going to happen, what is the water condition, what is the water content condition, and what's the effect of drought, and what is the effect of projection, right? So we run the model at you can say little column, little profiles throughout the world. We discretize it and run it independently, each one, and want to see the results, right? So this is this example, this is already published by my colleagues, Federico Maggi. So this is about simulating the water content, simulating the water content of the soil profile. So the soil profile is 1 meter, but it goes deeper into the water table because this is because you can simulate them, and you define it as the root zone as to 40 centimeter, and you run the model. So this is running the model 0 to 30 centimeter and also 0 to 100 centimeter for the period of 1970 to 2014 long-term average. So this gives us an indication about the water content, about what is the water average water content throughout the world under long-term simulation of the topsoil as expected. Okay, some of the dry region area have low water content compared with the tropics where we have a higher water content and so on, right? So then we can, so the top one is a 0 to 30 centimeter topsoil, and the bottom one is the 0 to 1 meter, okay? And when we compare, this is running using Brooks and Corey, and compare with saturation this is saturation index 0 to 1 and 0 to 1 using the FXW. It correlates quite well. The prediction, the maps of the water content correlates quite well. But what we can see that the Brooks-Corey tends to predict lower than the FXW because of it doesn't go quite to the dry end. So actually the soil is slightly wetter than it should at the dry end. At the dry end, so what you can see at the dry end is that you get more higher water content in the model. And we can model the geographic distribution of the dry and humid regions by identifying over that period, over 1970 to 2014. So how much of the area is it's below field capacity or above field capacity. Above field capacity is what they call as humid regions, and if it's below field capacity, that is the dry region all the time. So that's one thing that we can model and to see about the world. And then in the continental at the continental scale, so what we can model is that we can model for future climate. So we can model because there are layers of climate projections. This is an example. This is a climate projection from 2020 to 2030, 2030 to 2040, 2042. This one is the reference one is 2009 to 2018. And this is the future projection, next 10 years, next 20 years, and next 30 years. And the blue one, that means that positive change, that means the increased water, and the brown one means the losing water. So in this case, in Australian condition, we can see a lot of areas, except for the coastal area, you can maintain a little bit of more water, a little bit, but most of the area, then you would expect a decrease in water content. That means that there will be more drought. More drought is going to impact on the soil moisture storage, soil moisture storage. And then you can see also simulate about different crops. So if you're growing wheat, sorghum, maize, and cotton, and then the red one, that means that there's the change in the water content is going to be negative. The soil water content will be more negative. So for example, wheat, that over years that initially there's more of a positive budget, the blue one, and then with more and more time, then we expect to see that the wheat will require more water, and the drying climate that is going to affect on the productivity of the yield. And we can simulate that using mechanistic model. So the idea is that while we can do mechanistic model, usually we do mechanistic model, process-based model at one field, at one location, we do it correctly and we get results. But I think we can upscale this into an area. So it could be a region, it could be a country, it could be a continent, in order to get to see what is the impact of a larger scale. Larger scale could be a climate change, could be a agriculture implication, resources. I think that's a combination of a mechanistic model on empirical data that we can generate predictions of water retention curve, or we can generate prediction of hydraulic conductivity everywhere, but now we can use it in a simulation model because computer power now is very powerful. So now it is possible to run all this simulation throughout the region over 10 of years, over future projection and so on. And to close off, I want to show another example. This is another example where we can also run a carbon model. So this one is a semi-mechanistic model, not necessarily a full model, a semi-mechanistic model that we can run a soil carbon model on the landscape, and including erosion, right? So this is a Ross-C model, a kind of a new, not a new, a different Ross-C model, which is called Ross-PC1, because the Ross-C model usually is a single layer. The Ross-PC1 is a profile layers that contains layers, and each layers it has different pools. And the Ross-PC1 is made up of different layers, and there's transport, there's that you can increase, then you can put carbon organic input, and then the carbon can be moved over to the second layer of one. So this is the Ross-PC1. So it's semi-mechanistic because it's not fully mechanistic model, so it has some empirical parameters, but we combine it with a soil redistribution module in a landscape. So what do we mean? So that this is again a representation of pixels, and one of this is one profile, but within this profile we can run erosion model. We can simulate erosion. So at one place, if this is a profile and there's an erosion, then we lose some thickness, and that thickness transfer to another pixel. So this is the original pixel, and then that pixel transfer to another pixel, and we can see that now the new profile is getting thicker, and there's also more carbon input in this pixel, right? So this is simulating soil carbon, but also incorporating erosion. So erosion is a process, but erosion is not just about losing materials. So you lose materials here, but another pixel gains material there as well. So we can now simulate it using, first of all, this is digital soil maps of carbon, and we can run simulations about the historical simulation, what's happening in the past, so that it matches what's happening. And without this redistribution, without erosion and redistribution, we can see the soil carbon stocks overall in the area. It tends to overestimate, but incorporating erosion, then you can see some of the carbon is get transported elsewhere and it's being eroded. So now we can, using this model, once it's calibrated, we can take it to the future scenario. So it can have different scenarios. So if it's a constant land use, then what is going to happen if you keep using the same land use? And this is going to simulate at different climate change scenarios. And we can see that under different climate change scenarios, under constant land use, you can still have some impacts of up and downs in the carbon stock, but relatively stable. But if you keep increasing the cropland area, that means that some of the area you would have a decrease in the carbon stock compared with the business as usual. That means that the climate doesn't change, and you can see that there's an impact of that. So using process models, applying it spatially, so applying erosion and so on, that you can, I think it's going to be a powerful scenario modeling, so that we can assess on the impact of climate change, the impact of agriculture and resources on different scales. So I think it's about that. So as a summary, empirical models in digital soil mapping has become operational. So it's most people can do it, empirical models. So we can run predictions of clay, silt, sand, and then you can take it further. You can apply pedotransfer functions, and you can predict water retention curve parameters on different areas. You can spatialize it. But I think the next task is to use mechanistic model in the spatially. That means that in order to account for different spatial variability, you can use mechanistic model, process-based models such as hydros or any models that to take to account that the soils vary spatially. I think that is going to give a powerful assessment. I think that's my presentation.
Thank you, Dr. Minasne, for such informative lecture and using newer concepts to understand the soil processes in a better manner. May I request our panelists to, if you have some specific query, you may ask. I hope Dr. Minasne will agree to respond to those queries.
It's high pressure, lots of pressure.
No, sir. Dr. Sahu, are you there? Hello?
Yes, I am here. It's a wonderful lecture.
So if you have some specific query, you may ask Dr. Minasne, so that everybody will be benefited.
Professor Minasne, very happy to hear a lot of updates from your previous lectures, what I have been hearing. And congratulations for wonderful work. Only question for me is, you have seen somewhere in spatial scale modeling for soil organic carbon using Landsat data of different time series. And from there, you have predicted soil organic carbon and gone for the time changes. So could you see the accuracy, if at all you have a long-term experiments with respect to organic carbon stock in the soil on a X1 date and or X1 year and X2 year, and from your predict how accurate they are with respect to the change, which you could do or simulate using remote sensing data. It's a very interesting work, provided we get a reliable product for that purpose. Thank you.
Thank you, Dr. Sahu. Yes, very nice question. So Yes, I think yeah, we have to know also the limitation and also about the how, because what remote sensing can see is just the change in the vegetation and the probably land use or vegetation. But what it cannot see is underground, like how much carbon is contributing and how much biomass is removed, or what its contribution of soil carbon. So I think it's a simulation. I think at the point scale, probably you cannot expect to get a very accurate results, but I think at the larger scale, what you can see is the trend, the regional trend. I think that is more important than the absolute results. I would say that it can give an indication in the area whether if something serious is happening, or if something needs to be done. I don't believe you can get very accurate prediction for every year, but I think you can get a good indication about the trend for a long period of time, let's say 2 or 3 years, or 5 years to 10 years.
So, what is that? Those factors we should take care to bring down that gap for what we have from the simulated results and in the realistic scenario, because only it will be appreciated provided we get a realistic scenario. So what are those concerns, issues, research issues which we should address so that we match with the realistic world?
Yeah, I think more observation, calibration data, I think it's useful. I think having some actual measurement based on long term, if available, some long term sites, I think to calibrate the model, I think that's useful. I think that's going to give us a guide whether our model is on the right track, or if it needs adjustment. I think ground data is still very useful, and also it's good to always check the model whether it's performing well or not. But I think with increasing remote sensing data, I think we should make use of it in more creatively. I think rather than relying on empirical model, I think we can model it more on a mechanistically.
Yeah, thank you very much, Professor Buddhiman. Wonderful lecture.
Thank you very much, sir. Dr. Devashish Chakraborty, are you there?
एप्लीकेशन इतनी जिसमें लिखा था कि मैं एक्सटेंशन
Hello?
के बाद अप्लाई करिए ऑफिस
Dr. Devashish,
आपके एक्सेल
actually Dr. Devashish Chakraborty, he's a national fellow and he works on pedotransfer functions and meta-analysis. I hope he's not there. Dr. Mansingh sir, do you to ask some questions?
No, it's okay. I'm done. Thank you.
Thank you, sir. One of the student of Dr. Sahu, Bhavani Mandal, he recently completed his PhD on digital soil mapping. I wanted some questions from student side because it is very beneficial. If Mr. Mandal, are you there? Okay, I hope he's not there. Okay, then if any questions comes in future, then okay, Priyavrata Santra, a question comes from one of our delegates. What is the final application of transfer function? He is a principal scientist from Kajri Central Arizona Research Institute, Jodhpur. The question is, what is the final applications of pedotransfer functions in field, in soil redistribution model? No, just different. The question is, what is the final applications of pedotransfer functions in field.
Thank you. So I think for Dr.
Santra.
Santra, I think we generate a lot of pedotransfer functions. I think the next stage is I think we need to use it in actual simulation. I think and especially I think we have built we know the pedotransfer functions already, and I think we need to use it. Especially that means that within a field or within a region, we need to model how the hydraulic properties change, and then we need to run simulation models to see what is the effect of our management or climate change or any other simulation that you want to see. I think that is more useful, more functional, more useful than just have a pedotransfer function. I think this is the next stage, is that we take that pedotransfer function to actually use them in the simulation model.
Okay, thank you, sir. There is another question by Dr. Justin George. He wants how the pedotransfer functions can be used at what scale, and can they be used in soil erosion models also?
Okay, the soil redistribution module, I think it depends on the application. I think it can be used in the field scale or a watershed scale. So obviously on the field scale, watershed scale, I think the resolution needs to be finer to capture more detailed erosion processes. So the module that I use, we make it ourselves, but I think the thing is that things like RUSLE is that it only models erosion, it doesn't model deposition, right? So I think you need to have more mechanistic model that models not just erosion, because erosion just assumes that the soil disappears, right? Then I think you need to have erosion models that just move the soil, and it also models deposition.
There is a question by Dr. Nishant K. Sinha from Indian Institute of Soil Science, Bhopal. He's asking, is it possible to develop generalized pedotransfer functions which can be applied across the globe?
Yes and no. I think the question is that I think it depends. I think you can have a general pedotransfer functions that it's general, but I think it works sometimes, but I think it will also have limitations. So if you have local data, obviously it will be more accurate than the general pedotransfer function.
Okay. Thank you, sir. If any further question comes, we'll send you through mail and we'll get response from your end. And thank you very, very much for this wonderful lecture. Thank you very much.
Thank you.
Once again.